Hello, everyone. Welcome back. Today, I'm going to be talking about probability distributions. So, this is actually day one of Unit 4, and this is more about probability, but this is a specific kind of subgenre of probability with distributions. Now, I do want to also mention we're not going to learn about all the probability distributions in this course. And the reason being is because calculus and vectors is not a prerequisite for this course, and there's multiple high school level and university level calculus applications that do go into a lot of probability distributions. And so for today we're and for generally in this course we're only going to do focus on ones where we don't actually need that calculus element, where we can do the distribution, we can figure out the distribution without using any calculus techniques, right? Because there is no calculus in this course. This course will remain calculus free for us, okay? But we will learn about all the probability distributions that we are able to. I just wanted to point out that there are going to be more moving forward into the future as well. These are not the only ones. This is not the end all be all for distributions, what we learned in this course. It just isn't. So, what is a probability distribution? Well, to define a probability distribution, the probability of each outcome must be determined, right? To construct a probability model, a numerical value must be assigned to each outcome, and the result of the numerical value to a real life occurrence is called a random variable and is denoted by x. So x represents a set of all possible outcomes, which are represented by a number. So that may have made sense to some of you, maybe it didn't make sense to others. So I'm going to go through an example in hopes that showing this example will give some insight on this. So here's an example one of a probability distribution. It says, determine the probability distribution for tossing a coin twice by letting random variable x represent the number of heads and take the value of 0 for two tails, 1 for ht or th, and 2 for hh. So basically what this means is we want to know the probability that if we if we toss a coin twice, that we will get, what's the probability we'll get 0 heads, right? Because let x represent the number of heads. X is the number of heads. I'm going to reiterate that here. It's very important. So what's the probability we get 0 heads? And then over here, what's the probability we get 1 head? And what's the probability we get exactly 2 heads? So this is a distribution that tells us how likely we are to have various different outcomes, various different numbers of heads. Okay, so let's think about that. Well, if we get 2 tails, there's a 1 in 4 chance of getting 2 tails, right? Because going back to our sample space for what could happen if we toss a coin twice, we could either get 2 tails, or we could get heads tails, or we could get tails heads, or we could get heads heads. Those are the 4 things that could possibly happen here, right? And so what's the probability of 2 tails? Well, that would be 1 in 4, right? Because there are 4 things in our sample space in all, right? And there's 4 things in our sample space in all, and only one of them involves not getting heads at all, which is the tails, right? Now, what is the probability of exactly 1, right? Exactly 1 heads. Well, 2 out of 4, right? Because we have heads, tails, and tails, heads. So there's 2 ways for that to happen out of the total number of ways, which is 4. And we can simplify this further to just say it's 1/2. So there's a 50-50 chance that we will get exactly 1 heads in this experiment. And then what's the probability we'll get 2 heads? Well, another 1 in 4, right? There's one way to get 2 heads, and there's 4 total possible outcomes that we could have from this experiment. Okay, and also all outcomes, I should mention, all of them are equally likely, and so that's not something we have to worry about as to what's more likely than what, because getting a tails versus getting a heads, so they're both equally likely, right? Good, so that's our distribution. Now we could go further and say what's the probability of 3 heads, 4 heads, 5 heads, and so on, but they would all be 0, right? Those probabilities would all be 0 because if we're only flipping the coin twice, the maximum number of heads we can get is 2. And so if we were to add 3, 4, 5 to our x, the answer would just be 0. It would just be, there is no way, it's impossible. There is no way to get 3 heads when we're only flipping our coin twice, right? Or tossing our coin twice. Good. Okay, so let's get some terminology out of the way as well. The, the function p with brackets in it x, p of x, of the random variable x is called a probability distribution. The sum of probabilities is going to be 1. So basically what this notation is telling us, just a reminder of summation notation, actually that was our very first lesson of this course. What this is saying is that if we add up all the different probabilities for all the different possibilities for x, we should get 1. And that makes sense, right? Because there is some outcome that is going to happen, right? And so the probability of some outcome happening, p being any of the numbers, is going to be 1 because it's certain that one of them is going to happen, right? And if we go back to our example here, if we add up 1/4 plus 1/2 plus 1/4, we do get 1. And so we know that we've accounted for every single possibility. If we add up the probabilities of all of it and we don't get 1, either there's other random variables for x, right? There's other x values, so to speak, that we need to consider, or it means that we've calculated some of the probabilities incorrectly. And the same goes for, let's say we add them up and they're greater than 1. That also is a problem. It needs to be exactly 1, not greater than 1. If it's greater than 1, then that likely means that we double counted or made some sort of clerical error like that, because all the probabilities need to add up to exactly 1. Not greater than 1, not less than 1, but exactly 1. Good. Okay. So here's an example. It says, find the probability that x equals 1, or find the probability, p of 1. Okay? So let's say that p of 1 is equal to 0.5. Then we're told when an experiment is performed over an infinite amount of time, the quantity that we can expect is called the expected value. So what is the expected value, right? The expected value is when we take each value and multiply it by each probability to get the average. The expected value is also known as the average, right? So over here we established that probability of getting 1 would be 0.5, right? Or 1/2, we said earlier, but 1/2 and 0.5 are the same. We could rewrite all this in decimal form, and that's fine. Here they're asking us to find the expected value. So to find the expected value, what we must do is we need to say, well, we're going to multiply 0 by 0.25, right? So 0 times 0.25, and we're going to add that to 1 times 0.5, and we're going to add that to 2 times 0.25, and we're going to add all this up. Now, there's a couple ways to understand why this is. So one way is to just look at the formula and say, well, we're basically taking all the x values, which are 0, 1, 2, right? 0, 1, 2, and we're multiplying them by the px of I values. So, the probability values, which are 1/4, 1/2, and 1/4, or 0.25, 0.5, and 0.25 again. And we're taking those, we're multiplying them together, and then we're adding up those results, right? So that's quite literally what the formula says. Another way we can look at this is it's a way to find the average number that we'll get, right? By saying, well, we're going to get 0.25, of the time, a quarter of the time. So we need to multiply that 0 by a quarter. And then we're going to get 1/2 the time. So 1 times 0.5, on average. And then plus 2 times 0.25 to get 0.5 again, right? To say, and then we end up adding all these together and we get 0 plus 0.5 plus 0.5, which is 1. So that means our expected value, the value we're expecting to get, that average value is going to be 1, right? Which means we're going to get a heads and a tails. And that makes sense if we think about it, because what's the middle, right? What's the middle of those outcomes? it's getting one of each. And the outsides are 0 and 2. So either we get 0 and 2, and those are equally spaced, right? Those are equally likely and also equally spaced from 1. So those two other things would also average out to 1. So if we think about it, it makes sense why the average would be 1, because we have equal chances of getting a little bit above or a little bit below 1. And then we also have a chance of getting 1, and of course adding 1 to itself and dividing by the number of ones also is going to give us 1 for the average, and so on. And so this makes good sense as well, that that was going to be the average. So think of expected value as the average. Now, something else I want to note with expected value, it doesn't actually have to necessarily be a value that's here. So let's say we got like 1.5, for example. Even though 1.5, it's not possible to flip heads 1.5 times. Even though that's not the correct answer in this scenario, 1.5 could be an answer in some scenarios regarding flipping our coins or rolling our dice or things like that. And so it doesn't actually have to be an exact value. What 1.5 indicates is that our expected value really is likely 1 or 2, right? Is equally likely to be 1 or 2, or that kind of thing. That's really what we're expecting, is things that, or whether it's 1 or 2 or other numbers, things that average out to be about 1.5. So things that are close to that value, as close as can be. All right, here it says to represent the probability distribution in graphical form. So let's do that. Here I'm going to say this is our P of X axis, like that. Here's 0.5 and here's 0.25. And then here's 0. So 0 would be here. Then we have 1, and then we have 2. So 1 is like that, and 2 is like that, right? And so there's our graphical form, right, where we have the 0 and the 2 come up, and the 0.5 and the 1 come up to 0.5. So it's twice as likely that we get a 1 than that we get a 0, or twice as likely we get a 1 than we get a 2 as well. So this also, if we look at this graph and I asked you to find, what's the middle point of the graph? What's the middle? You'd probably also say, well, it's 1 and 0.5, right? That's this point here. Looks like that's our middle point, where we get 1 as our answer. Happens more often. And also everything else is evenly spaced on either side. Good. All right. So let's try another example using kind of the same methods we just learned, okay? So this next one says, suppose, is it going? Okay. It says, suppose that the random variable x has the probability function given by the table. So it looks like the probability of getting a 0 is 0.5, okay? So 50-50 chance that we're right off the bat that we're going to get 0, right? Or what about 1? There's a 25% chance that x is 1. There's a 0.125 chance, so a 12.5% chance that the x is 2, and also a 12.5% chance that x is 3. So this one clearly isn't really evenly distributed amongst the different things. It's not going to average out to a nice value necessarily. Okay, so here it says find the probability that x is 2, or find p of 2. Well, P of 2 is equal to 0.125, right? And how do we know that? We know that because this part of our table, it tells us. It says that when x is 2, the probability is 0.125. And so we're basically here just copying that off the table. So question 1 is not so bad. Then they ask, find the expected value for the probability distribution. So we know what to do. We need to multiply all the x's to the probabilities, and we need to add those values up. So our first one would be 0 times 0.5 plus 1 times 0.25 plus 2 times 0.125 plus 3 times 0.125, right? So it's a weighted average, right? We're taking the average But certain values count for more than other values, right? Like we're more likely to get a 0 than anything else, and we're more likely to get a 1 than to get a 2 or a 3, right? And so this is our weighted average. We're weighting it, and so this answer is going to be a lot closer probably to 0 and 1 is what we're expecting the expected value to be. It's probably not going to be that close to 2 and 3 because 2 and 3 only have a small chance of actually occurring, right? So let's do it. Here we get 0 plus 0.25 plus 0.25 again plus 0.375. Awesome. Which is 0.875. Good. And that's about what we expected because even though the most likely thing to occur is 0, and this is a bit closer to 1 than it is to 0, we also have to account that there's a small chance, there's a 12.5% chance for 2, and another 12.5% chance that it's 3, right? And so those values having a little, a small probability that 2 and 3 could be the case, well, a relatively small probability compared to the other probabilities in the distribution, that those are kind of pulling this number up a little bit, getting it closer to 1 than to 0 because we do have those possibilities there as well. And so that's good. That's about what we were expecting. And even though 0.875 is not an x value, that is okay. The expected value does not have to actually be, a nice round number. In fact, most of the time it will not be. It'll be a number between the numbers to kind of give us an idea, right? It's the weighted average. Okay. Now it says to represent the probability distribution in graphical form. So this is also pretty simple, just like the last time. We just have to draw our x values. Here's our p of x values, and here's our x values. And we want 0, 1, 2, and 3 this time. And we want to go all the way up to 0.5. So let's see, let's do 0.125, 0.25. And I guess that would make this 1.5. Okay, so this one will go up to here, and this would be 0.375. Okay, so this one would go all the way up to here. This one would go up to here, like that. This one would go up like that. This one like that as well. So as you can see, we have much more, it's much more, we have more points, right? We have higher probabilities on the right than we do on the left, right? And so it's going to be a number closer to the left rather than the right because we have more, right? Which makes sense with what we found out over here for our expected value. Good. All right, let's do one more example, which is example 3. Example 3 says a game consists of tossing 2 coins. If the result is 2 heads, you win $1. If the result is a head and a tail, then you win 50 cents. Okay, not bad. And if you toss 2 tails, you lose $2. So here it says to define the random variable for probability distribution and list the probabilities for each random variable. Okay, so in this case, instead of representing the number of heads or tails gotten, which is what we did for example 1, this time I want x to represent amount of money won. Let x represent the dollars won. Okay, and I'm also going to put in brackets here that negative means loss, right? Because if we're calculating the amount of money won, right, if we put a negative in front, if it's actually a negative number, that means we lost that much money, right? So what are the different things we could possibly win or lose? Well, we could lose $2, or we could win 50 cents, or we could win $1, right? And so overall, the question is this a winning game or a losing game, right? Are we expected, if we play this game enough times, are we expected to overall win and we should just keep playing the game over and over again, we can make infinite money? Or is it a losing game, right? If we just play this, hundreds of thousands of times, are we eventually going to just, lose a bunch of money? Or is it a fair game, right? Is it a game where if we play this a million times on average, we're going to come out even? We won't have lost or won any money. And let's see if that's the case, right? So let's finish this up. It says here if we lose $2, there is what chance, or I should put here instead of y, I should put probability um, of that happening. So what's the probability we lose $2? Well, the probability of losing $2 is the same as probability of tossing two tails, right? Because when we toss two tails, we lose $2. So that's going to be a 25% chance. Okay. Now, what about winning 50 cents? Well, we win 50 cents if we get a head and a tail. And how often does that happen? Well, that happens half the time, according to our previous calculations. And what are the odds, or what is the probability that we win $1? Well, that's going to be 25% chance, because when do we win $1? We win $1 when we flip two heads. Next, it says find the probability that x is 0.5, right? So what is that probability that x is 0.5? Well, this tells us, right? This chart we just made, it tells us that the probability of winning 50 cents is 50%. Now, that's just a coincidence that it's the same thing for both. It won't always be. But in this case, the probability of winning 50 cents is actually 0.5, right? Half the time. We keep playing this game 100 times, about 50 of them, about 50 of those times, we will have won exactly 50 cents. Good. Okay. Then they ask, what is the expected value for the probability distribution? And so this is where we're going to find the weighted average and figure out, do we expect to lose money playing this game, or do we expect to win money playing this game, or is it a fair game where, if we played it thousands and thousands of times, on average, we wouldn't win or lose any money, right? Let's figure that out. So let's do the expected value. It's going to be -2 times 0.25 plus 0.5 times 0.5 plus 1 times 0.25, which is equal to -0.5 plus 0.25 plus 0.25, which is 0. Okay, so the fact that our expected value is 0, that tells us this is a fair game, right? That this is a game that if we played this thousands and thousands of times or millions of times, however many times, we are expected to long-term break even, right? We're not expected to win the game or lose the game. So therefore it's, unless we enjoy having fun playing this game for whatever reason, it's not really a game worth playing, because we don't actually win any money from it. Although at the same time, we also don't lose any money from it, which is good as well. It's a fair game with fair probabilities here. Okay, well, that is everything for probability distributions part 1. Next time, we'll talk about uniform distributions. So I hope everyone has a good rest of your day, and we will see you tomorrow for uniform distributions. Bye, everyone.